Hello once again and welcome to this slide video from the Cornish Radio Amateur Club for the advanced certificate leading to the full license. So today we're going to have a look at propagation, and that will be 3 questions in the current syllabus. So you'll expect 3 questions on propagation out of the 62 in the exam. So let's have a look at some of the items in the syllabus. 6A1 says, recall that an EM wave comprises E and H fields. By EM they mean electromagnetic. E and H fields in phase, at right angles, and at right angles to the direction of travel. Recall that in circular polarization, the polarization of the wave rotates as it propagates with either a right-handed, clockwise from behind, or left-handed polarization. Recall this is often used for satellite communication where the orientation of the satellite is indeterminate. Recall that the transmit and receive antennas should have the same polarization. And 6A2 says, recall that under free space conditions, electromagnetic waves travel in straight lines and spread out according to an inverse square law of power flux density, and that the field strength measured in volts per meter drops linearly with distance. So that's not all of the syllabus items, but let's have a little look at those first. And let's start by looking at what is a radio wave. Well, in a radio wave, there is a direction of propagation, and that's shown by the mauve arrow on your screen. And at right angles to the, we should say that the velocity of that propagation is the same as the speed of light, 3 times 10 to the 8th meters per second, and it's not much difference in vacuum and in air. It'll be slightly slower in air, but not very much. If you've looked at the feeders video, we look at the velocity factor of various types of transmission lines, and for example, we see that in polythene called polythene dielectric coax, we get a velocity factor of about 2/3. So in coax with a solid polythene dielectric, the radio wave propagates at only 2/3 that of the speed of light, and we need to make adjustments to feeder and antenna lengths to take this into account. Anyway, returning to the radio wave, we've got the direction of propagation, and the E and the H fields are right angles to each other, and also the direction of propagation. So here we have the E field and the direction. So you can see that they're at right angles. There's a little schematic at the top showing that relationship, the electric field, E, and the direction of propagation. Now we can add in the H field, and it's a bit difficult to draw this 3D representation on a 2D screen, but if you can imagine the H field, or the magnetic field, coming in and out of the screen. So the H field is at right angles to both the E field and the direction. So if we look at one wavelength there, I've taken it between 2 peaks, so that's 1 lambda at this particular frequency, between 2 peaks. Now the polarization of this wave is, by convention, the direction of the E field. So if you imagine a quarter wave antenna vertically mounted on the roof of a car, then the magnetic waves would be coming out as, if you like, rings in the horizontal direction, but the E field would be vertical, the same direction as the antenna. And it's also worth noting that the relationship between the E and the H fields is constant, and one does not exist without the other in a radio wave. It is, of course, possible to have an electric field without a magnetic field, for example, in a capacitor, and a magnetic field without an electric field, for example, in a transformer. But they are coherent in a radio wave and one does not exist without the other. So let's have a quick look at fields radiating from a transmitter. Here on the left we have a transmitter and on the right a receiver. And if we switch on the transmitter, then a field will radiate out from the transmitter to the receiver. And you can see there that the E field is, this is looking at them side-on view, the E field is going alternately vertical, and then vertically in the up direction, and then vertically in the down direction, and then back vertically in the up direction. So this remains in the same plane, but the direction goes 180 degrees about each cycle. And of course, if we were to show the H field on the same diagram, we would see the H field alternately going into the screen and coming out of the screen. And that's shown on the little depictions above those three waves there, the last three waves before we get to the receiver. So, going back to the syllabus, we need to note that the power flux density in watt per meter squared spreads out in accordance with the inverse square law. And if we have a look at this, that depicts a globe or a sphere with radius r, then the formula, and you don't need to know this for the advanced course, this is just background, the formula for the surface area of a sphere, A, is equal to 4 pi r squared. So you can see that as r increases, the area increases with the square of the radius. And this is what's happening then with the power flux density. As we have a point source there, perhaps the isotropic antenna as a little point source there, and you can imagine it as light, and it's illuminating a globe, first of all, of radius r, and then it's illuminating a globe of radius 2r, then the area has gone up by 4, but the power at the center of the sphere hasn't increased, it remains the same, but it's spread over 4 times as much area. So here we can see then that as the radius of the sphere increases, the illumination in terms of power decreases with a square law, inverse square law relationship. However, the field strength in volts per meter squared is just inversely proportional to the distance. So if you had a field strength meter, you would see at twice the distance only half the field strength. So in the exam, make sure if you're asked one of these questions, you find out whether it's power flux density, or you note whether it's power flux density in watts per meter squared, in which case it spreads out in accordance with the inverse square law, or whether it's field strength, and that's in volts per meter squared, and that's just simply proportional to distance. So if the distance doubles, the field strength halves. And here we can show it mathematically. Power flux density is proportional, that's a little fish sign, to 1 over distance squared, and field strength is simply proportional to 1 over distance. Or another way of saying that is power flux density is inversely proportional to distance squared, and field strength is inversely proportional to distance. So there's a possible examination question, and you do need to note whether it's power flux density or whether it's field strength in the question that's posed to you. So let's have a look at polarization, vertical and horizontal. Well, we said earlier on that it's the electric field that determines the polarization. And if it was vertical polarization, it would be like the preceding slide, and if it's horizontal, the electric field will be coming in and out of the screen. Now, circular polarization, the electric field is rotating. The E vector and hence the H vector rotate as the wave propagates. And that's depicted there with the rotating arrow. Now, with circular polarization, the whole vector, the E and the H, both rotating either clockwise or anti-clockwise, as seen from behind, complete one rotation every wavelength. And that's an important thing to note. And we can have right-hand circular polarization or left-hand circular polarization. And why do we have circular polarization? Well, it's very useful for satellites where the polarization of the satellite is indeterminate. And if you had a low Earth orbit satellite coming over the horizon, and if it had a horizontal antenna, if you like, if it was angled down at 45 perhaps, as it came over the horizon, but not directly overhead, as it passed over, you could see that the apparent polarization of that antenna would change as it disappeared over the horizon on its next orbit. And therefore it's difficult to decide what sort of antenna either to point at the satellite for the best reception. But if you have a circular polarized antenna, that obviates that problem. So, moving on, let's have a look at some more syllabus items. 6b1, understand that the ionosphere comprises layers of ionized gases and that the ionization is caused by solar emissions, including ultraviolet radiation and charged solar particles. So here we are moving on to HF propagation. Recall that the ionospheric layers D, E, F1 and F2 and their approximate heights. That's something you have to memorize for the exam, and there'll be some diagrams in a minute showing those, but they're also given in the book in chapter 11, the book Advance. 6b2 says, recall that the E layer can reflect radio waves and that sporadic E is caused by areas of highly ionized gas that can refract waves in the VHF band. Recall that the E layer supports single hops up to about 2,000 kilometers. And I have seen questions where they talk about the distance between a transmitting and receiving station, and they might say, for example, that its propagation is by the E layer and it's 6,000 kilometers. How many hops? And so you need to say 3 hops. Now, 6b3, 4 and 5 we'll deal with later. 6b6, recall that the D layer tends to absorb the lower radio frequencies during daylight hours and that it tends to disappear at night. Understand that if the D layer absorption occurs at frequencies higher than the maximum usable frequency, or the MUF, then no ionospheric propagation can occur. And 6b7, recall which emitter bands will be open to support ionospheric propagation at different types of the day and year. So let's start off by getting an orientation of the Earth's atmosphere. So, the layer that we live in and spend most of our lives in, if not all of our lives, is the troposphere. That's the layer where the terrestrial weather takes place and in which aeroplanes fly. And in that layer, most of the communication is by ground wave, and so probably the VHF and above frequencies. And it extends from the surface to between 10 and 15 kilometers in height. At the poles, the troposphere is flatter due to the Coriolis effect, so it will be at a lower level, and at the equator, the troposphere extends up a little bit further. But there is no weather as such above the troposphere. In fact, if you see a cumulonimbus cloud, a big thunderstorm cloud, the classic anvil shape, then the flat top of it is cut off by the top of the troposphere. It doesn't extend into the layers above. So that's where all the weather takes place. Above the troposphere is the stratosphere, and that extends up from up to about 50 kilometers, from either 10 or 15 kilometers the lower level, in other words the top of the troposphere, up to about 50 kilometers high. Now in the troposphere, as you go higher, the normal effect is that it gets cooler, and it cools down about 1.5 degrees centigrade per 1,000 feet. In the stratosphere, the temperature no longer gets cooler, it stays at a steady temperature for just about the whole stratosphere. Above the stratosphere is the mesosphere, and that extends from about 50 kilometers up to about 80 kilometers. And above the mesosphere is the exosphere, which takes us up to the limit of space, and that extends up to about 400 kilometers, from about 80 at the bottom to about 400 kilometers at the top. Now, just to get an idea where we are, we're at the very fringes of space here, and when we look at the ISS, the International Space Station, that's orbiting just above the exosphere in space at about 408 kilometers high. So even at the top of the exosphere, there'll be hardly any molecules of air, and even fewer to collide with the ISS and slow it down in its orbit. Nevertheless, unless it gets an orbital boost from time to time, these molecules will eventually slow it up so that it would re-enter. And we saw that with the Mir space station. Way above the ISS, we have geostationary satellites, such as the ones we use for watching digital TV. A geostationary satellite is in an orbit that rotates at exactly the same speed as the Earth rotates, and so from the ground it appears stationary. That's why our TV dishes and also communications dishes for the Intelsat series of satellites don't need to be trackable, don't need to track the satellite. They can just point to a fixed point in the sky where it appears that the satellite is always there. In fact, it is always there because it's geostationary. And that's 36,000 kilometers up, typically, or thereabouts. And so you can see there's a huge difference between the low orbit satellites that are just on the fringes of our atmosphere and the geostationary satellites, which are much further out in space. Now, we don't need to know any of this for the advanced course, but it does help our understanding as we go through this presentation. So you don't really need to know anything about, except that the troposphere is there, and that's the only term that you need to remember, but it's useful, as I say, to have an orientation. Now, within the mesosphere, then above the mesosphere into the exosphere, we have the ionospheric layers. Now, these ionospheric layers very much affect HF communications. And starting at the bottom at 80 kilometers, we have the D layer. At 120 kilometers, the E, and the E sporadic, and we'll be talking about that much later in the presentation. But just for now, let's think of it as the E layer. At 200 kilometers, the F1 layer, and at 300 to 400 kilometers, the F2 layer. Now, we need to memorize these because they may well come up in the exam, or questions related to them may come up in the exam. So, in the early morning, the sun comes up at a particular point on the Earth, and when the sun comes up, it emits, or the UV rays that are emitted ionize the upper atmosphere. And these layers that we talked about, the D, E, F1 and F2, are layers of ionized gas. And they're ionized by the charged particles and the ultraviolet radiation from the sun. The degree of ionization depends on the time of day at any particular point on the Earth. If the sun is overhead, the ionization will be greater. If it's summer and the Earth isn't tilted away from the sun at the particular point that we're considering, so in England it would be, if it was summer, there'd be more ionization. Or if there are solar ejections, sunspots or gas ejections from the sun, more charged particles are produced, and that causes an increase in ionization. And this can be quite significant. It is worth noting that whether the day is sunny or not has no effect. So down where we live and experience our lives in the troposphere, whether there are clouds or not makes absolutely no difference, because these ionized layers are way, way above the troposphere, as shown in previous slides. So sometimes we say that the ionosphere depends on space weather, and by that we're implying that it's not affected by terrestrial weather. So the sun's come up and a layer starts to form and become ionized, and we've shown it there on the graphic. And first thing in the morning, it'll form, there won't be much ionization because we've just left night, and these layers are very temporary and transient in nature, and after the sunlight stops, they fizz away and disappear. So first of all, we'll get high level layers ionizing, and then as the day sets in, the ionized layer will come down. And here we've shown it coming down to 80 kilometers into the D layer. And when this happens then, signals coming up at MF and in the low HF bands will be dissipated or attenuated to the point of extinction in the D layer. And we call this D layer absorption. So we can say that medium frequency and lower HF frequencies suffer D layer absorption. This is why we don't get medium wave broadcasts under normal conditions from France during the day. It's because the D layer has established, and the medium frequencies, particularly, which and to a certain extent the lower HF frequencies, are simply absorbed by the D layer, and therefore don't make it across to the UK. Now, normally, D layer absorption happens with frequencies of less than about 3 to 4 megahertz, but it can extend if the D layer is very, very ionized, as high as 14 megahertz. Now, as the sun has continued to ionize the layers during the day, then the F1 and F2 layers have also, particularly the F2 layers, have also become ionized, as have the layers in between the D and the F2. And so higher frequencies are able to penetrate the D layer. These are the ones above the 3 to 4 megahertz mentioned before, and are refracted off the F2 layer, making long distance communication possible. So the communication station on the right is able to communicate with a station on the left over great distances. There is also a ground wave that travels out, and it's shown going to the sailing boat in the sea there. And that will happen over a short distance, because that wave will be attenuated as it travels around the Earth. The attenuation is at a minimum over water, but it's still significant. It is at a maximum over land. The higher frequencies will not be absorbed by the D layer, but refracted by the E or F layers. So that's just restating what's happening here. Now that's a higher frequency, and two things depend on whether it's refracted or not. One is the frequency, and the second is the angle of incidence, the angle with which it hits the F2 layer. The shallower the angle, the further it is likely to go. Now, the lowest frequency that successfully penetrates the D layer and is refracted back to the receiving station is, for a particular path, is the LUF, the lowest usable frequency. And there we've shown it with a yellow graphic. It's going through. You can see some attenuation has taken place, but enough signal has got through to the F2 layer to make it back down to Earth at the receiving station on the left. So that's the lowest usable frequency. And if we were to draw a graph of that in July for a transatlantic path, let's say over to the east coast of the USA, you can see then that as the sun comes up at about 5 o'clock in the morning in July, the upper atmosphere, the D layer, I beg your pardon, starts to become ionized, and after that, until about midnight, the lowest usable frequency is 10 megahertz. So frequencies below 10 megahertz will simply be absorbed by the ionized D layer. And that's because it's July, it's summer, the days are long, and over that path there is considerable ionization of the D layer. And in fact, it's only between about midnight and 5 that lower frequencies can be used that are not absorbed by the D layer. And it's during that time that you might hear MF or low frequency HF stations. If the frequency is too high, it won't be refracted to the receiving station. So here, we've picked a frequency that's too high. The degree of ionization of the F2 layer isn't enough to refract it back to the receiving station. If we turn the frequency down a little bit, let's say that was 29 megahertz, and we turned it down to 28 megahertz, we might find then that the signal was in fact returned. And the frequency that is just returned to Earth at the receiving station is the MUF for that particular part, the maximum usable frequency. So there, in this example, in this graphic, we might have seen 30 megahertz or something passing straight through the F2 layer and going off into space, but 28 megahertz being just low enough to return back to Earth. And that's the maximum usable frequency. Now, if this was a path that we wanted to communicate over, we wouldn't select, ideally, the maximum usable frequency to communicate. We would probably select something called the optical frequency for the optimum frequency for transmission, the I think, OFT rather, OFT. And that's normally about 85% of the muff. That's because if we selected the muff, then any small disturbances in the ionosphere would mean we'd lose the signal. We want to pick a frequency as high as possible because we don't want it to be attenuated by the D layer too much. So the higher the frequency that we select, the less attenuation or absorption in the D layer. However, if we pick it too high, it'll just carry on into space. So if we pick it at about 85% of the maximum usable frequency, we get the best of both worlds. A stable signal, hopefully, but without too much attenuation. So UK to East Coast USA. Let's have a look at a possible graph there for the maximum usable frequency. If you remember, the previous graph that we had showed the lowest usable frequency, and here we show the maximum usable frequency. And we can see then that from midday on to the early afternoon, we can use higher frequencies because the F2 layer is more ionized and our signal won't simply pass through the F2 layer. But it takes until 10 o'clock, for example, until we can start to get above 15 megahertz. Now, here we have them combined, the two graphs, the maximum usable frequency and the lowest usable frequency. So the maximum usable frequency in green and the lowest usable frequency in red. And it's only between those two, the luff and the muff, that we're able to communicate. So for example, at 6 o'clock in the morning, we're unable to use 17 megahertz. And we're unable to use about 4 megahertz. But at 4 o'clock in the afternoon, we're able to use 17 megahertz, but we're not able to use, let's say, 7 megahertz because it's below the lowest usable frequency. So it's in the band between the red and the green traces there that you're able to communicate. And it's up towards the green trace that we should ideally be selecting. Of course, we're limited to the bands that we're in, but that would be the ideal case. So communication on a given path is only possible between the luff and the muff. And it's worth noting that these are not universal graphs. They don't count for every path that we're considering. They're specific to a path, and this path is specifically, this example is specifically the UK to the East Coast USA. If we were looking at the UK to South Africa, which is directly south of us, then there would be different shapes to both of those curves. But we are required for the examination to just understand the general shapes of the curves, and so you should be able to at least memorize that one, at least reproduce it in its broadest sense. So in winter, there's a shorter period of D-layer absorption, and the maximum usable frequency varies more than in summer. So in winter then, when the Earth is at our location, the Earth is tilted away from the Sun, then the incident sun on the atmosphere above us and above the path that we're considering from the UK to the East Coast USA is less. So it's not until 10 o'clock that we start to see significant D-layer absorption. And by 10 o'clock in the evening, when it's starting to get dark, the days are short, then the D-layer absorption quickly disappears. Similarly, because the days are short, the higher level, the F2 layers, only start to become significantly more ionized around mid-afternoon, and because our ionization level isn't very, very high, we can use frequencies up to 40 megahertz. So again, the July and December graphs that you've just seen, if you can sort of sketch those from memory in the exam, that might also help you. If we look at a path to Australia, and I don't think we need to be able to reproduce this one particularly, but we know that the path to Australia will involve multi-skips because the Luff. So here we see that path, and it's a complex path because it's happening over a big area of the Earth's surface with different illuminations. But what we can say here with this graph is that for considerable parts of the day, communication is not possible to Australia because the Luff is greater than the Muff, and therefore there is no window for us to operate in. Now, it's worth also remembering, and here it is, UK to Australia in December. So we need to recall also that the F2 layer provides the furthest refractions for HF signals, about 4,000 kilometers, and that the F layers combine at night. So some questions will say there's a path over, say, 20,000 kilometers. How many hops or how many skips have taken place? So you simply take 20,000, divide it by the 4,000. So there'd be five hops. And associated with that, 6b3, recall that multiple hops permit worldwide propagation. And we also need to understand how fading occurs and its effect on the received signal. Well, one of the points that is in the syllabus is that at night the F1 and the F2 layers merge and become indistinguishable. And I've shown that in the graphics with a slightly thicker layer of ionization there at F1 and F2. So you could say that really it extends then from 200 to 400 kilometers. And we had a look at a path that's using the F2 layer there, F1 and F2 layers combined. It would look something like that. And as per the syllabus, we can think that that could occur for up to, say, 4,000 kilometers. That would be a sort of maximum length that we might achieve for a single skip. Other skips then would allow us to have transglobal communications. So paths can be up to 4,000 kilometers long using the F2 layer. But the same signal can arrive at the receiver by two different path lengths, and this will cause fading. Here we can see that at a different moment in time, the same signal, at the same instant in time, the same signal might be diffracted by two clouds of gas that have slightly different densities. And so the path length for the white signal and the yellow signal can be slightly different. And this will result in slightly different phases which will either reinforce or cancel at the receiving station. And this effect can happen either rapidly or slowly over time. And this is fading. And here we've shown a second hop taking place. 4,000 kilometers for the first hop, and that would be received by the first receiving station. But 4,000 kilometers later on, other people will also be able to receive it. So back to the syllabus, we need to recall that the highest frequency that will be refracted back to the transmitter is known as the critical frequency of vertical incidence, or the critical frequency. Now we'll have a look at that in a minute. It's related to the maximum usable frequency, but instead of beaming your signal off into the distance and trying to achieve a low angle of incidence onto the ionosphere, the signal is beamed up vertically, and there are test stations called ionisons that perform this function. Recall that the highest frequency that will be refracted over a given path is known as the maximum usable frequency, MUF, and that this will be higher than the critical frequency. It'll be higher because the angle at which the signal arrives at the ionosphere, instead of being directly incident on it, it'll be at more of a glancing angle. Recall in general terms how the MUF varies over a 24-hour cycle and the variation in MUF from summer to winter. And we've looked at the graphs in doing that. So now let's have a quick look at the critical frequency of vertical incidence and what that means. Well, let's see how it's measured. And again, you don't need to know this for the advanced course, but it's good background to see what's happening. So an ionosonde sends a vertical pulse of HF at different frequencies up vertically to these layers, the F, the E and the D layers, as shown on the graphic on the screen. And the ionosonde antenna will be a log periodic, in other words, it'll have a wide frequency range, and instead of pointing roughly parallel to the Earth's surface, as you would expect with HF antennas for communications, it'll point straight upwards. And there it is, it sent a signal up, and the round trip time for the return pulse is measured, and that establishes the height of the reflection point. Now this is, if you like, an HF radar, but looking vertically upwards instead of horizontally. So in this example then, we've sent a signal up at 2 MHz, and it's reflected off the E layer at 100 kilometers high and returned to Earth. So let's have a look and see what happens at 1 MHz. At 1 MHz, we send a signal up, but because of layer absorption, we get nothing back. And although we'd be expecting something around 100 kilometers high or 80 kilometers high, the circle shows that we've got no trace back where we would expect it. So that's just absorbed. If we increase then to 2 MHz, and you can see the arrow on the graph has increased to 2 MHz, well, slightly above 1 MHz, we've started to get returns from the E layer. And the 2 MHz penetrates the D layer and is reflected by the E layer. So we start to get a trace on our graph, on our ionogram. So there it is there. And we similarly go up to 3 MHz. That penetrates the E layer and is starting to be reflected by the F layer. And then we carry on increasing the frequency, and we get a trace something like that up to 6 MHz. And the interpretation of that trace allows us to determine the heights of the E, F1 and F2 layers at a particular time of day. Now, specialist stations for this exist around the world, and they're used to assist the predictions used for HF communications. So when we talk about the critical frequency, for the purposes of this exam, we're talking about the frequency that we send up that will still be reflected back to Earth, and that's probably off the F2 layer. Now you might say, well, that must be the same as the maximum usable frequency, but that isn't the case, because if we have a path from A to B, then the angle of incidence will be a lot shallower on the F2 layer, which allows us to use higher frequencies. So we can always say that the MUF is always higher than the critical frequency, but and additionally, rather, we can say that it can be 2, 3, or even up to, I believe, 5 times greater. So returning to the syllabus, we can say 6b7, recall which amateur bands will be open to support ionospheric propagation at different times of the day and year. And for that, questions will be posed on the 3.5 and 21 megahertz propagation over a 24-hour cycle. So memorization of the graphs there for summer and winter for MUFs and LUFs between the UK and the USA will assist you to be able to solve any questions in the exam. Recall that the ground wave has a limited range due to absorption of the energy in the ground, and that the loss increases with increasing frequency. Now, we looked at the ground wave travelling out to the yacht from the receiving from the station on the right. We said that it would be ground wave attenuation would be less over water than over the ground, but that the higher the frequency, the greater the loss. So you can experience this quite, or you can relate to this quite easily, because long wave transmissions, in other words, very low frequencies, VLF frequencies, travel a great distance, and that's why long wave was used in the old days for broadcast radio, and it would be not uncommon to be able to get ground wave, long wave transmissions from France, for example. The availability of frequency of spectrum in long wave, of course, is limited, and the distance over which it travels is great. So that can be a problem for people engaged in frequency planning. But similarly, you know that at HF, for example, top band 1.8 megahertz, the ground wave can travel a fair distance. But you know that at VHF the range becomes limited, and at UHF more limited again. And this is because the ground wave gets more attenuation when it's close to the surface. So our normal sky wave then travels off one of the ionospheric layers. A ground wave then travels directly to the receiving station, but the distance over which it travels will be far less than the sky wave. And between the two, then you will get an area which is called the skip zone or dead zone. And these are 3 definitions that you need to remember for the exam: the sky wave, the ground wave, the skip zone or dead zone. The skip zone or dead zone is the area in which no communication is possible. So, for example, with the container ship shown there from the transmitting station on the right, it is impossible to have communication. However, further on at the receiving station on the left, the sky wave makes it, because of the refraction of the ionosphere. So sky wave, ground wave, and skip zone or dead zone. So bands open or closed. Again, go back to the these ones that we showed you for July and December. And as I say, if you could just be able to sketch those, that would be helpful for you to interpret any questions that are posed in the exam. Now, we talked about the E layer, and we talked about sporadic E. Sporadic E is a phenomenon that affects VHF. And here, if we have a highly ionized layer, especially in summer, in the E layer, then we find that VHF can bounce off the sporadic E layer, not just VHF, but in fact, we'll go through the bands that it affects in just a second. And communication is possible up to 2,000 kilometers, and you need to remember that figure. Remember, 4,000 kilometers for a skip off the F2 layers, and 2,000 kilometers for sporadic E. And sporadic E affects or signals are refracted, refracts signals on the 10 meter, 6 meter, 4 meter, and 2 meter. So 10 meter is not strictly a VHF, it's 28 megahertz roughly for our bands anyway, or 30 megahertz if you took it exactly. So it's just into the VHF bands and going up to about 150 megahertz, 144 megahertz for us. So questions there may talk about signals being received in summer, unexpectedly on 6 meters over 2,000 kilometers or something like that, and then the question there relates to sporadic E. Right, let's have a look at some others. Here we've got a tropospheric or space wave. So if we're looking at frequencies above 30 to 40 megahertz, in other words, into the VHF band, and we have a transmitter on the left and a receiver on the right, and we've drawn our curvature of our Earth and assumed an Earth with a normal radius, the radius of what it is, then the signal from the transmitter on the left doesn't make it to the receiver because we don't have optical line of sight. And so the signal hits the Earth and is attenuated so that it can't be received at the receiver. But in fact, these signals travel a bit further than optical line of sight. They bend around, they follow the curvature of the Earth slightly, they diffract around the Earth. But rather than curve the signal line, we actually just flatten the Earth slightly to make it easier to do path planning. So instead of drawing an Earth with a normal radius, we draw one with a radius of 1 1/3 times what it would be. And that means we get a flatter curve for the Earth, and for the same path then, we now have the transmitter managing to send a signal to the receiver, and it's unobstructed. And that radius, or the apparent radius of the Earth, we call K, and I don't think we need to know that, but it's just background. So here we have a signal, and we've said K equals 4/3. Optically, you wouldn't be able to see the transmitter from the receiver or vice versa, but from a radio point of view, you can. Now, if there was a hill in the middle with K equals 4/3, then unfortunately the signal wouldn't get through because it would hit the hill. But if it was a mountain or a building perhaps with a knife edge, we get something called knife edge diffraction, and this happens above about 70 megahertz. The signal from the transmitter goes out and hits the peak, and then, if you like, scatters into a number of directions, one of which will make it to the receiver. So this is another mode of propagation above about 70 megahertz called knife edge diffraction. Another more esoteric mode of propagation, and I don't think we need to know much about this. It hasn't got a hat next to it in the book Advance, and it isn't mentioned in the syllabus, but we'll cover it anyway. Is where we get meteors entering the atmosphere and ionizing the atmosphere, and this is predictable as to time of year because there are various clouds which are the remnants of dust left by passing comets in the Earth's orbit, and as the Earth intersects with these, they manifest themselves as meteorites or shooting stars. So what happens is that during the ionization, briefly, communication is possible, but communication is very brief. Ducting, if you get a negative lapse rate or temperature inversion, it can trap the radio wave in a layer. It's often associated with high pressure. So the duct establishes between two radio stations, which are not normally able to communicate because they're obstructed by the curvature of the Earth, but the duct traps the radio wave and steers it around the curvature of the Earth. If you like, it acts as a conduit. It reflects alternately off the top and the bottom of the duct and is trapped and therefore reaches the receiver. And a sea surface duct is close to the surface of the sea. In this example, the received antenna is too high and a better signal would be obtained lower down. So here we've got a very low duct. The signal goes through, but because the receive antenna is high up, because it is perhaps on rising land or on the top of a hill, it doesn't receive the signal. However, if we lowered the antenna down to nearer sea level, we would suddenly pick up a signal. So that just about summarizes propagation. Thank you for listening, and good luck with your examinations.